I'll probably make some more explanation videos concerning this one, but the power of stellar metamorphosis is incredible once you start to really understand what it means. Um, yeah, transformation curves. I'll link this to the bottom, this paper. If you guys want to follow along, I'll explain what all this means. Stellar metamorphosis, transformation curves on the Wolinsky-Taylor diagram. Hi, Celeste. Now, the purpose of a transformation curve isn't to necessarily, predict things. It's just sort of to give the idea that these objects that we're studying, they have deep evolutionary histories, or metamorphic histories, I should say. And with astronomers, they sort of look at it as, well, if something is this mass or if something is that mass, it can be classified as this or that. But that completely misses the picture. The reason why I did these transformation curves is because nature is vastly more complex than what the astronomers are telling you. Not only that, but transformation curves allow us to explain why there are so many different rocky objects that are different sizes. Why are all these different sizes? Why? Why do some of them have iron nickel cores? Why do some of them have atmospheres? Why are some of them more rocky and less metal dense? Why are some of them have deep oceans covered in ice? Why do some of them have thin oceans like the Earth, but have huge iron nickel cores? Astronomers don't really have an explanation for it. They just say, well, the rocks clump together in certain areas and that's that. The explanation they have doesn't even exist. And the reason why these are all different sizes and levels of differentiation in the amount of material that they're composed of is because they're all stars, the remains of stars, that have gone somewhere along this transformation curve. Now, assuming all these stars start out really big, hot, and bright, the transformation curves are very close together. Now, each individual star will have its own transformation curve. It'll evolve slowly on the top, or it'll evolve really fast on the bottom. And the faster and faster it goes, the smaller and smaller object it will make. And a really small object that remains maybe of like Oberon or Titania or Iapetus or Phoebe or Charon, the object that orbits Pluto, or even Pluto itself. These objects were destroyed long before they had enough time to collect material to form the object in its interior. So they were essentially hot Jupiters that were orbiting around a very hot host star and were ripped apart before they could form the object in their interior. And then their host star either kicked them out or kept them there for a long period of time, and they just been in orbit around each other for a very long period of time. A good example would be like the moon and Earth. I think the moon has probably been in orbit around the Earth for at least 4.5 billion years. The Earth-Moon system is one of the oldest systems in our solar system. And believe it or not, the sun to the planet system, the Earth orbits the sun, it's a very young system. And we know it's young because the sun is very young. And it has much older objects orbiting it. Essentially, you have solar systems upon solar systems upon solar systems that have evolved or been disintegrated many tens of millions, hundreds, tens of billions of years ago. And I'll go ahead and review this real quick. Some beginning statements here. Each star has its own unique transformation curve. No star is the same. They can look similar, like human beings, or like, trash pandas, or danger noodles, or, orcas. But they're all different. They're all unique. Each star can have a very similar looking transformation curve when they are very young, but the transformation curve will deviate as the star has different orbital histories. So for instance, you could have two stars start out really close together at the very top, and one will all of a sudden take up orbit around a hotter host really, really close, and then it will go along this red curve, and it will start evolving down here, and the other one will separate and form the new object in its interior very, very slowly. So you could have two stars that are the same age. That's where that little cross number is right here, these two little cross numbers. They could have two stars that are the exact same age for the most part, and have two incredibly different masses. One will have the mass of Neptune, and then one will have maybe the mass of Pluto. But they'll be the same age, but totally different masses, all because the transformation curves turned out to be different. An analogy would be like, babies that are born, and then one baby has like a huge inheritance from a very rich uncle that happened to die, and they get, hundreds of millions of dollars in some fund that they can't touch until they turn 35. And the other baby is born in some poverty-stricken area of Africa, and they end up having to mine diamonds and get those blood diamonds, and they're never going to ever get rich, ever. Yet they both have, the exact same beginnings. I know it's kind of a shitty analogy, but so they're the same age, but vastly different end result in the long run. And that also means it becomes more pronounced as time continues. So for instance, you have a very massive object on that cross right there, and you have a very small object right here, same age, but the transformation curve will probably continue on, and they'll age the same amount too, but then the mass difference will become even more pronounced as time goes on. So I guess the money, financial wealth analogy still holds. The rich are going to get even richer, and the poor are going to get even poorer. But crappy analogy, I know. As well, you can go on the horizontal axis. So, for instance, these little black dots right here, it says two objects can have the same mass but be in completely different stages of evolution. They're on different transformation curves. Right here, these two little black dots. And of course, everybody knows that mass is on the y-axis, and age is on the x-axis. So you could have stars that are this very, very similar mass, these two little black dots, but be wildly different in age. One will be far, far, far older than another. And notice the very young object is on a quick evolving or quick transformation curve, and the other one is on a transformation curve that's a bit slower. Of course, if they evolve even slower, then you would move over to the left even more, or would that be the right? Yeah, the right. And you would have even a more pronounced age difference. So what this means is, if you have a rocky object like the Earth on a slow transformation curve, and you have an object that's similar in mass to the Earth, it could be less evolved. It could be very, very young compared to the Earth. So essentially what it means is that when astronomers, when they look at objects, say you have hypothetically, I don't know, I don't remember if I tried to calculate their age or not, but Ganymede and Callisto, two of Jupiter's moons. If you had those objects as being the same mass and both in orbit around Jupiter, Now, they're not the same mass, I know that, but they're both in orbit around Jupiter. Let's hypothetically say they're about the same mass. Astronomers, what they'll do is say, well, they're both in orbit around Jupiter. They both have similar mass, therefore they're probably the same age. But that's totally false. Ganymede and Callisto have different evolutionary histories. They could be wildly different in age, even though they both are in orbit around Jupiter and they both have very similar mass. I remember I wrote another paper with Jupiter's Io. I think Io is extremely young. I think Io was probably, in comparison to Ganymede and Callisto, I think Io was probably the most recent object that Jupiter had adopted when Jupiter was a red dwarf and ripped Io apart, like when it was a gas giant, so it couldn't even form anything significant, not even an iron nickel core, but it still has its sulfuric outer crustal layers, which was the new forming planet, but it had its atmosphere ripped already before it could form anything of significant size in comparison to the Earth. So essentially, when you're looking at Io, don't look at it as, oh, well, the iron nickel core has to form at exactly the same size. Remember, Io didn't even have enough time to form its iron nickel core. So here's Io and here's Earth. And Io was ripped apart way too quickly. It was on a very fast transformation curve, and Earth was on a very, very slow one. It had enough time to, form life, form water oceans, yada, yada, yada. But, let's see, I have some more notes here. Oh, yeah. Okay, let's go through these. If you guys want to read along, of course, I've linked it to the bottom. There are no stepped transformation curves, they are continuous. The differences between transformation curves are not discrete and static, but continuous and dynamic. There's a big habit that astronomers have and mathematicians have, is where they try to take something and they make it discrete. Think of stairs, like to a building. You step up or down one stair, and you step up down another stair, and you go back up another stair or whatever, and it's in discrete steps. It's jagged. But that isn't how transformation curves work. Transformation curves are smooth, they're continuous, and they can speed up and slow down, but they're not going to be jagged. There isn't a staircase there. It's very smooth, and it's continuous. Let's see, number 3, transformation curves are not the entire history of the star, but can be used to make a guess of their future and infer their past. I know I previously said you can't use it to predict, but you kind of can in a way. This theory isn't that advanced yet, but I think that's a path people can take when they start to research the differentiation of the star itself and reverse engineer the layers, and figure out, was it in orbit around a hotter host during this time or this time? Kind of like looking at rings to a tree. More work will need to be done in the future to elaborate this. Of course, if anybody wants to work on number 3, go for it. I've been too lazy. Number 4, you cannot have a star on a transformation curve and move that star to the next higher transformation curve. If anything, the star can either remain on its curve or drop down. It cannot go back up. Think about it like a check valve used in plumbing. Fluid can go in one direction, but if it tries to flow backwards, the ball or valve disc will stop it. So think of transformation curves as being like invisible check valves, where as the star is moving down, it can't just go up this direction, or it can't go backwards. It can't sit there. An Earth isn't going to become a Neptune, in other words. It's a Neptune that's going to become an Earth. You can't go in the reverse direction. The fact that a star cannot gain any significant mass to move up to a higher transformation curve is outlined in the principle of mass loss, which takes part after the extreme blue giant phase of stellar evolution. It can gain mass, though, just not more than it loses. This is outlined in the principle of mass conservation. Something that has net mass loss will become less massive. It's easy. You take a bite of a cheeseburger, the cheeseburger is going to become less massive. You don't sit there and take a bite of a cheeseburger and then the cheeseburger get more massive. That would defy reality. But of course, I I think astronomers know how to do that very well. Number 5, the similarities of transformation curves is closer the younger the star, and the similarities can decrease statistically as they grow older and evolve. The red, yellow, green, and blue curves on the graph were all led from much larger, hotter stages of evolution, but they all lost mass in different amounts as they aged for various reasons. They can be the same ages but have different masses, different levels of differentiation, different atmospheric thicknesses, etc. Of course, that has to do with being able to reverse engineer the star itself in its most evolved stages. The biggest differences being like when you study the moons and the rocky objects. These are huge clues. These are huge stellar fossils, if you will, and being able to reverse engineer these objects, you can determine what their pasts involved. Just saying that they just formed from a bunch of rocks coming together is very 20th century. Stars can be the same mass, but this does not necessarily mean they have the same levels of differentiation, atmospheric compositions, and thicknesses. I went over that. The graph outlines the fact that you could have two stars the same mass, but one be 4.8 times older than the other, meaning 3.5 billion to 17 billion. I already went over that. I already went over the cross symbol. I went on top Jupiter. Okay, I'll go over number 9. The term ice giant would be a star, Neptune and Uranus, that orbits so far away from a host that has more time to build up an inner core, the future Earth, and has more material to work with before the atmosphere is completely lost. So these would be on a slower transformation curve. So essentially what I'm saying is, if astronomers find an exoplanet, an evolved star, very, very distant from its host, it's building up that planet a lot more than an object that would be really close and it's losing its atmosphere. So just by looking at a exoplanetary system, which is a polymetamorphic system in the previous talk, the objects that orbit really close, those are the objects that are on a very fast transformation curve, especially if it's around a hotter host, like a blue giant, and it's just ripping it apart, and it's not has to have a time to build that planet in its interior. But if you have an object really far away, like Neptune and Uranus, it can orbit very slowly. It's nice and calm. You know, it can build up its interior and has lots of time. So those objects are going to be more likely to form the larger Earth-sized objects, and Jupiter and Saturn, those two. But if the sun somehow loses those objects, they go in orbit around a hotter host, there's a big chaotic event happens, say, for instance, a red dwarf would enter on our system and throw everything off, then all bets are off. Those objects could take up orbit around a hotter host and get ripped apart and move down a lower transformation curve, making a much smaller object. Okay. 10. The transformation curves are ideal at the moment and have more refining to do. What has happened, though, is a new paradigm of stellar evolution is being made, counter to dogma, yada, 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 yada. 11. As is noted, stars cannot have their ages set to host stars because they are highly evolved stars themselves, as noted in the general theory in the graph above. A companion star can be vastly older than its host. This is evidenced by all the highly evolved stars in our system that are vastly older than the sun, and some even older than others. It is impossible for them all to have formed in the same disk. They are just too different now, and all have past histories that are also different, as is evidenced by their physical and orbital characteristics. I don't know if you guys realize this, but astronomers, when they see a rocky object in orbit around a sun-like star, they assume the rocky object and that sun-like star are the same age because they're in orbit around one another. I don't know who allowed that kind of theorizing to propagate in the sciences, but it doesn't make any sense. Makes as much sense as me visiting a retirement home. It's just because I'm talking to my grandma, I'm the same age as my grandma. It doesn't make any sense. The objects that are in orbit around a hotter host that are more evolved are older than the host. So forcing them to be the same age that needs to go away. All right, guys, this talk is almost reaching 20 minutes. I'll link this paper to the bottom. If you have any more questions, feel free to ask. Of course, I'm going to talk about this more if somebody asks more questions. All right, later.